Let's continue with our discussion on suspended growth reactors. In the previous session, we conducted the mass balance for generic component A for the biomass separator configuration, and used the matrix method to compile the stoichiometry and kinetics for the components of interest in a simple setup. Aerobic CSTR treating a single organic substrate with a single group of biomass. With the matrix, we can find the reaction term Ra in the mass balance for each component. We then learned the conversion of TSS and VSS based stoichiometry and kinetics to COD based ones. Recall the general form of mass balance in the biomass separator configuration. Remember that we're designing for steady state performance. At steady state, accumulation equals to 0. Let's find out the mass balance for active biomass, XBHT. In the subscript of X, B indicates that it is the active part of biomass. H suggests it is heterotrophic, as organic carbon are used as substrates. And T indicates that it is TSS based. For this simple setup, there's no biomass in the influent. Biomass grows as soluble substrate is consumed. Due to the biomass separator, no biomass goes to the liquid stream effluent. All biomass goes to waste stream. Because the active biomass XBHT is TSS based, let's convert it to COD based first. To find the reaction term RXB, we can utilize the stoichiometry and kinetics matrix. So we can multiply the stoichiometric coefficient by the process rate for the growth of XBHT. Then do the same for the decay of XBHT. And finally, add them together. After dividing both sides of the steady-state mass balance by XBHT times IOXBT, we get this expression. Recall the description for solids retention time, SRT. For the biomass separator configuration, SRT is V over FW. We can transform the mass balance by dividing both sides by FW. So the growth rate μh equals to 1 over SRT plus specific decay rate BH. The growth rate can also be expressed by the Monod equation. Rearrange the equation, we can calculate the effluent soluble substrate concentration based on SRT with given half saturation coefficient K sub S, maximum growth rate, and specific decay rate BH. When we have infinitely long SRT, all biomass is retained in the reactor. There's no biomass wastage, only decay. Then the specific growth rate equals to the specific decay rate at steady state, and the effluent substrate concentration is the lowest possible value that can be achieved with this reactor configuration. So 1 over theta C, or 1 over SRT, approaches to 0. We can write the expression for S sub S minimum to K sub S times BH divided by mu hat minus BH. During design, we can compare the discharge target with this S sub S mean value. If the target is even lower than S sub S mean, a different reactor configuration is needed. When the specific growth rate is a function of the influent substrate concentration, this specific growth rate is at its highest possible value, and this indicates that there's no substrate degradation in the reactor, and the SRT is too short, causing the biomass being washed out. From the maximum growth rate, we can calculate the minimum SRT, which causes biomass washout. Although there's no minimum HRT, because there will be degradation as long as biomass is retained in the reactor. It is dangerous to have an HRT lower than the minimum SRT, in case that the biomass separator fails. Similar to the mass balance of biomass, we can write the steady-state mass balance for the soluble substrate, S sub S, which is already in COD terms. But note that the yield YHT is used with a unit of gram TSS biomass growth per gram COD substrate consumed, because the active biomass concentration XBHT is in TSS terms. After simplifying, we know that HRT is V over F, so we can further transforming it by dividing both sides by F. This gives us the expression for active biomass concentration from substrate reduction, yield, specific growth rate, and HRT. Because we know that in the biomass separator configuration, the specific growth rate is 1 over SRT plus specific decay rate, we can substitute that to express the active biomass concentration XBHT determined by substrate concentration reduction, yield, specific decay rate, HRT, and SRT, all of which are known constants or design parameters. For a bioreactor that does not separate biomass from liquid, such as a conventional anaerobic digester, HRT equals to SRT. So we can further simplify the active biomass expression to this. We can also write the steady-state mass balance for debris which is generated from decay process and removed from the bioreactor. Therefore, we can find the relationship between the debris concentration and an active biomass concentration from the mass balance. The active biomass concentration can be substituted from the previously shown expression. Note that because of the active biomass concentration is expressed in TSS, the debris concentration should also be expressed in TSS. Because in reality, it is difficult to measure the active biomass and debris separately, the TSS measurement includes both. So we introduce the total biomass, which is a combination of active biomass and debris. We can write its expression from previous equations. Again, if the reactor does not separate solids and liquid, so HRT equals to SRT, then the expression for total biomass concentration can be simplified into this. And we can define the active fraction as the active biomass concentration divided by the total biomass concentration. Can you pause the video and try to write out the expression for the active fraction? Okay, so after canceling out most of the redundant parts, the active fraction is only determined by the stoichiometry and kinetics of decay process FD and BH, as well as the solids retention time. As we have covered previously, the observed yield is the total biomass growth per substrate consumed, considering the cell decay and maintenance. In the biomass separator configuration at steady state, there's no biomass in the influent, and all biomass grown and decayed are wasted. So the total biomass growth is the total biomass concentration times waste stream flow rate. The total substrate consumed is the difference between influent and effluent substrate concentration times the influent flow rate. FW over F actually equals to HRT over SRT. So we can substitute the total biomass concentration and can simplify the expression for observed yield into this. The observed yield is higher than the true yield as it includes the stoichiometry for decay. The unit for observed yield is gram TSS of total biomass generated per gram of COD substrate consumed. Recall that when ammonia is used as nitrogen source, and all energy generated is used for cell synthesis, the fraction of electron from electron donor goes to cell biomass equals to the true yield. Similarly, when decay and cell maintenance is considered, Fs equals to the observed yield.